Hi everyone. So to wrap up our discussion about proofs involving sets, we've considered when is X an element of a set, when is a set a subset of another set, and the last case is how do we decide if two sets are equal to each other. And in some sense, there's nothing new here because, as we'll see, this is kind of like the relationship between an if-then statement and an if and only if statement, because for two sets to be equal is the same thing as saying that each is a subset of the other. So let's look at that more closely. So just to reiterate, if I say that two sets A and B are equal to each other, that's the same thing as saying that X is an element of A if and only if X is an element of B. Remember that two sets being equal means they have exactly the same elements. And that's what this says. It says that the elements of A are all elements of B, and the elements of B are all elements of A, so they have exactly the same elements. If you decompose this a little bit, this if and only if statement can be split up into two implications. X in A implies X in B, and X in B implies X in A. And so the assertion that A and B are equal, since this implication is just a way of saying that A is contained in B, and this implication is just a way of saying B is contained in A, then what we've shown is that A equals B is equivalent to A contained in B and B contained in A. So proofs where you try to show the two sets are equal follow the same kind of structure as proofs of if and only if statements, namely first you prove one direction and then you prove the other. And you can't forget either direction or you're going to be in trouble. So to go back to Euclid's algorithm, we actually, buried in that long discussion, we did prove two sets were equal. So here's the proposition that we proved. Let D be the greatest common divisor of two natural numbers A and B, and let M be any integer. Then there exist K and L such that M is AK plus BL if and only if M is a multiple of D. This was in the second part of the proof of Euclid's algorithm. We showed that you know that you can solve this equation by the only times you can solve it is when M is a multiple of the greatest common divisor. And in that case, you can solve it. If you want to think about this as a statement about sets, let's let A and B be natural numbers and let D be the greatest common divisor of A and B. And then we can define two sets. One set is the multiples of the greatest common divisor. And the other set is the collection of things of the form AX plus BY. And what Euclid's algorithm says is that these two sets, A and B, are equal. So to make this concrete, if A is 7 and B is 3, this says that the collection of things of the form 7x plus 3y, where x and y are in Z, is exactly equal to the set of multiples of the greatest common divisor. So D is 1 times n for n in Z, which is just Z. So in other words, in the case where A is 7 and B is 3 and the greatest common divisor is 1, we can interpret Euclid's algorithm as saying that the collection of elements of the form 7x plus 3y, as x and y runs over the integers, is exactly the integers themselves. And the two statements that are involved, to say that A is a subset of B, is to say that every multiple of D can be written in the form AX plus BY. So that's one inclusion. If you're a multiple of D, then you're of the form AX plus BY. The other direction says, if you're of the form AX plus BY, then you're a multiple of D. And put together, those imply, that's how you get that the two sets are equal. And if you go back and look at the proof of the second part, the uniqueness part of Euclid's algorithm, you'll see that we had step 1 and step 2, and they were basically step, I think 2a actually, and step 2b. They're actually these two statements. Let's look now at some other examples. So suppose we have two prime numbers. So a and b are prime. and we consider their multiples. So A is the multiple of the prime number A. And B are the multiples, big B are the multiples of the prime number B. So if you want to make this concrete, which is always a good idea just to look at an example, we could take A to be 3 and B to be 5, and then A would be the multiples of 3. So it would be like -6, -3, 0, 3, 6. And B would be the multiples of 5, so -15, -10, -5, 0, 5, 10, 15. And the claim that we're making here is that the intersection of these two sets is the multiples of A times B. Well, 15, for example, this is a multiple of 3, and it's in this set, so it does check out, right? That, just a few quick checks. 10 is in the multiples of 5, but it's not a multiple of 3. 15 is a multiple of both. So what this is saying is that if something's a multiple of two different prime numbers, then it's a multiple of their product. So what's involved in proving this? Well, we're trying to show that the set A intersect B equals the set DAB, D and Z. And so we have to prove two different things. First, we have to prove that A intersect B is a subset of DAB for D and Z. And that means that if X is in A and X is in B, that's what it means to be in the intersection, then X is in DAB, D and Z. So if X is in A, that means X is a multiple of A. And if sorry, I should have said Y. Oh no, intersection. If X is in B, then X is a multiple of B. So X is a multiple of A and X is a multiple of B. And now it's crucial that A and B are prime numbers, because what this is telling us is that both A and B appear in the factorization, in the prime factors of X. And therefore, A times B is a divisor of X. If A and B weren't necessarily prime, we've seen this example before, actually. It could happen that A and B have a factor in common, and so that they each divide X, but their product doesn't. But if A and B are both prime, like 3 and 5, then if we know that 3 is a divisor of X, one of the prime factors dividing X is 3, and one of the prime factors of X dividing X is 5, because the factorization into primes is unique, if 3 and 5 both occur, then their product has to occur. So 15 does divide it. And therefore, that tells us that AB is a divisor of X. And so what we've shown here is that AB X equals ABD, and therefore we've shown this inclusion. What about the other direction? I'm a little short on space. I'm going to skip to the end to do this. Whoops. Let's go way down here. So the other direction I need to show is that DAB for D and Z is contained in A intersect B. And that amounts to saying that if X equals DAB for some D, then X is in A and X is in B. In other words, if X equals DAB for some D, if then X is a multiple of A and X is a multiple of B. And remember, to be an A is to be a multiple of A, and I use D1 and D2 here because there's no relationship between which multiple. So they're different, they're new variables. And this is clear. This is actually an easy direction because we can take dBA, so that means X is a multiple of A, and X equals DAB. So if we take D1 equals DB and D2 equals DA, we show that X is in A intersect B. So putting the pieces together, we've shown that the set DAB is equal to A intersect B. So the crucial thing to remember there is that there's both directions involved. We got some more examples because I think this merits some practice. So now let's look at problem 17 on page 171. It claims that this is kind of like a distributive law for the Cartesian product, that A cross B intersect C is A cross B intersect A cross C. So the proof requires two parts. First, we show that A cross B intersect C is contained in A cross B intersect A cross C. In other words, we show that A cross B intersect C is contained in A cross B and A cross C. So to do that, we have to show that if you're in here, then you're in both of these. So let's let AX be an element of A cross B intersect C. So A is in A, and X is in B intersect C. Therefore, X is in B and X is in C. And so AX is in A cross B and AX is in A cross C. This is what we needed to show. This shows that A cross B intersect C is contained in A cross B intersect A cross C. Now, remember, there's always two parts. Now we show A cross B intersect A cross C is contained in A cross B intersect C. So let's let AX belong to A cross B intersect A cross C. So AX is in A cross B, which means that X must be in B, right? If it's an ordered pair, the first element comes from A and the second element comes from B, the second element must be in B. And the same argument shows AX is in A cross C, so X is in C. So therefore, X is in B intersect C, and AX is in A cross B intersect C. So this shows that A cross B intersect A cross C is contained in A cross B intersect C. So we prove that the two sets are equal. It's a lot of writing for a not very interesting fact, but nevertheless, it's actually not as kind of pointless as it might seem. Let's draw a picture. If you go way down to I'm going to make another picture. So the claim is that A cross B intersect C is A cross B intersect A cross C. So let's draw a picture here. Here's A. Here's my set A. I want to think of it as being on the x-axis. And let's use some other colors. So this is going to, that's too yellow. This is going to be my set B here. And how about orange? This is going to be my set C here. And this region here, this is B intersect C, where the two colors overlap. So one way to think about A cross B intersect C is that it's this rectangle. It's the points where the x-coordinate, so to speak, is in A, and the y-coordinate is in both B and C. A cross B, on the other hand, is the set where the x-coordinate is in A and the y-coordinate is in B, so that's a bigger rectangle like this. And A cross C is the region where the x-coordinate is in A and the y-coordinate goes like that. So, in fact, it's clear here that the intersection of the big rectangles is this rectangle, and that is the same thing as the Cartesian product of A with the intersection of B and C on the y-axis here. So maybe that explains a little bit about what is actually going on here. Okay, more examples. Here the claim is that the collection of elements 12a plus 4b, as ab runs through the integers, is equal to the collection of multiples of 4. And if you want to check this, I mean, think about A. If A is 1 and B is 0, you get 12. If A is 0 and B is 1, you get 4, and so on. So you could write down a bunch of things here. But I think this is actually easier, and let's just look at it directly. So let's do, as always, we have two parts. Part 1 is the 12a plus 4b for A, B, and Z is contained in the set of multiples of 4. And this is the assertion that if y equals 12a plus 4b, then, which is, in other words, if y is an element of the set on the left, then y equals 4c for some c in Z. And, of course, if y is 12a plus 4b, then it's 4 times 3a plus b. So let c be 3a plus b, and we see that y is 4c, and that gives us one inclusion, that every element of the set of numbers of the form 12a plus 4b, as a and b run through Z, is in fact a multiple of 4. A more interesting problem is the other direction. The other direction says that 4c is contained in the collection of 12a plus 4b. A, B. Maybe you think this is more interesting, maybe not. So what this says is that if x is equal to 4c, then x is equal to 12a plus 4b for A, B in Z. Well, that maybe isn't so hard because set a equal to 0 and b equal to c, and you get x equals 4c. And this shows, therefore, that 12a, anything of the form 12a plus 4b, anything of the form 4c is automatically of the form 12a plus 4b. Just take a equals 0 and b equals c. So these two sets are equal. And I think we've got one more here. Maybe a slightly, well, I don't know. Let's look at it. So A is the set of pairs xy squared, xy in R2, where y equals x squared. And actually, this has a nice geometric meaning. This is the collection, this is the graph of the parabola y equals x squared, right? Because the points on the graph are the points whose coordinates are x, y, where y equals x squared. That's what the graph means. So A is this graph. What is B? B is the set of z such that there exists x in R with xz in A. And the claim is that B is precisely equal to the set of positive real numbers. How do we interpret this one? Well, let's try some examples. Let's ask the question, is 3 in B? Well, to be in B, you have to ask, is there an x so that x comma 3 is in A? But x comma 3 is in A means 3 equals x squared. And so the answer is yes. 3 is in B because the square root of 3 is in A. And now maybe you see where this is going. Is -1 in B? Is there an x in R so that x minus 1 is in A? No, because -1 equals x squared has no solutions. And so what you can see here is that actually B, one way to think about B is that B is the collection of z in the real numbers such that the square root of z, such that z equals x squared has a solution in R. So if you want to prove that these two sets are equal, then to follow this process, first you want to show that B is contained in the set of z in R, such that z is bigger than or equal to 0. And to prove that, it's, I think, easier to show that if z is less than 0, then z is not in B. That's the contrapositive. The set of z in R such that z is less than 0, right? To show that if z is in B, then z is bigger than or equal to 0 is the same thing as showing if z is less than 0, then z is not in B. And given my remark up above, that's true because x squared equals z has no solution in this case. And to prove the other direction, we have to show that if z is in R, so now we want to show that z in R such that z bigger than or equal to 0 is contained in B, and that amounts to saying that if z is bigger than or equal to 0, then x squared equals z has a solution. in R, which is true. So again, there's two directions to check. If you don't see this point, I maybe glossed over this a little bit. Why is B equal to the set of Z in R such that Z equals X squared has a solution in R? That's something to think about very carefully, and I will leave it to you to do that.